Okay, we are going to take a look at this next section of Chemistry 30 in our organic chemistry unit called organic reactions. Now, essentially, up to this point, what we know is that we know that there can be a variety of different organic compounds. We know that there's a bunch of functional groups that we can combine with a carbon chain. And essentially what we're going to look at is the types of reactions that these carbon compounds can undergo. The first reaction that we're going to take a look at is called an addition reaction. Now, an addition reaction begins with an unsaturated hydrocarbon, which means that this is either the reaction of, an alkene or an alkyne. Again, this is a double or a triple bond. Okay, and essentially we have these unsaturated hydrocarbons and they bond with some sort of diatomic molecule. Now often these diatomic molecules are our halides, okay, or it can be a hydrogenation reaction and we have our hydrogen gas that combines with this carbon compound. So our example that we have here is either our alkenes and our alkynes. So in this example we have ethene, okay, so C2H4 plus a chlorine gas diatomic molecule, giving us chlorine attached to each of our carbons, and notice that we result in a single bond at the end. So if I was to draw this out again in a different way here, and I'm just going to do this in a new color, maybe if I can here. Here we go. So if I draw this out, I have ethene that looks like this. And what we see is when we add our chlorine, we get an addition. Now, essentially, we're literally adding in these two chlorine atoms into this compound. So we have C, our two carbons, with our chlorines bonded on carbons number 1 and 2, plus our two existing hydrogens. Okay, so our two chlorines here get added in here and here. Okay, so we have an addition reaction. Although we had to break bonds, we had added in a diatomic molecule to our carbon chain. Okay, we can also see addition reactions with water. Okay, so we have an alkene plus water, and that gives us an alcohol. Now, again, what we see here is that we have an alkene. This R chain, essentially what these R groups mean is that can be any other amount of carbons on either side. So the R and R prime, okay, that's what this little R with the tick here is. Okay, it can be the same or different alkyl groups, and isomers often result. So what that means is that this can be any level of carbons as well as this can be any level of carbons. And we're just looking at this component specifically with the double bond. So we have a double bond in between our two carbon atoms. We're adding water. Now, essentially, when we add the water, we add one hydrogen, and then we add one hydroxide, okay? So, or hydroxyl group. So what we do is we break this bond, this double bond, and we add in this molecule as a hydrogen and a hydroxyl group. So again, this hydroxyl group makes it form an alcohol. Okay, there's our two types of sort of general addition reactions. You will have to be familiar with addition reactions going into an exam or a diploma. So let's maybe take a look at a few examples here. Again, we have ethene. Let's take a look. We have ethene. This is what we just looked at actually. Okay, ethene plus chlorine. Again, this is chlorine gas, Cl2. And it forms 1,2-dichloroethane. So again, this is what we just saw. We see 1,2-dichloroethane. Notice again, because we broke that bond, it's ethane and not ethene. So this is our two chlorines. That's where those guys came from there. Okay, we have ethyne plus bromine. Let's take a look at what that looks like. Ethyne, meaning that we have a carbon, a carbon with 3 bonds, and then 1 hydrogen on each side. We're adding in chlorine, or bromine, bromine, which is diatomic as well. And we get the formation of 1,2-dibromoethene. Okay, so let's take a look. We have ethene, and we have 1,2-dibromo, Now, again, I would draw these sort of apart from each other. The chances of them going on the farthest angle is probably, or the farthest distance apart is probably more likely, just because they have repulsion based on their electronegativities, things like that. Our last example here is propene. Oops, what am I doing? Here we go. Propene. Okay, prop meaning 3, ene meaning there's a double bond, has to be off the first carbon. Okay, and we have like this. Something like that. Those are all hydrogens. Okay, and we're adding in hydrochloric acid. Again, this is diatomic, except we have hydrogen and chlorine as our two atoms. Okay, we form, then, 2-chloropropane. So essentially we break this bond, we add in on our 2 carbon, we add in a Cl, and because the bond broke in between our first and second carbon, that hydrogen is going to join up with our first carbon, and then the remaining hydrogens were already existing from our propene molecule that turned into propane. So we have 2-chloropropane. So you can see how there's addition reaction. You start with 2 molecules and you result in one final product. Okay, the next reaction we're going to take a look at is called a substitution reaction. A substitution reaction breaks a hydrogen-carbon bond in an alkane or an aromatic ring and replaces the hydrogen atom with another atom or group of atoms. So what we see here is if we look at our propane as an example, okay, we take the propane. Now notice again, we have an alkane. We're not dealing with an alkene or an alkyne. We're dealing with an alkane. And we add in a diatomic molecule, such as bromine. Now, often light is used as a catalyst for this reaction, so do be familiar with this going into a diploma, that substitution reactions often require light. Okay? I'll put that as a note up here. Often require light. Okay? So, what we see is when we add bromine, I think of this reaction as if we are substituting a player in a soccer match, for example, or any sort of sporting event where you might sub in a different player in hockey, whatever. So what we see here is, let's just take one of these hydrogens as an example. Okay, and we'll say that this one of these bromines, only one, okay, replaces one of the hydrogens. So this bromine and this hydrogen are going to swap. They're going to substitute each other. So what we see here is that we have a bromine in our new compound, and then we have hydrogen that binds with bromine. So we have HBr as a product. Now, because in this example that we have here, we see that we are using propane. That means that this bromine can be added either onto carbon number 1 or carbon number 2. So the chances are that we could have 2 separate molecules. We could have 1 bromopropane or 2 bromopropane. Okay, regardless of where that bromine gets substituted in, either if it's on the first carbon or if it's on the second carbon. Okay, it doesn't matter as long as we see that we only have one of the atoms in our diatomic molecule, such as bromine, that is added into a compound or our carbon chain molecular compound. What we see then is that because these two switched place, our hydrogen and our bromine, did a little swap like so. Okay, what we see here is that we get a result. Instead of 2 hydrogen atoms being displaced, we just have 1 being displaced, resulting in hydrogen bromide. Okay, so substitution is like subbing a player in some sort of sporting event. You just switch spots, you switch the locations of those 2 atoms. Okay, so we can see them with halogens. Okay, again, halogens is a great example to look at substitution reactions. Okay, we get alkanes and aromatics, whatever it might be. Light, again, notice light is used, okay, as sort of like a catalyst, like I mentioned. And we get organic halides. So in this case, we have, looks like, let's draw this guy out. Oops. Hydrogens here. Looks like we have 1 chloroethane, and we're adding in a diatomic molecule like chlorine gas, and we get a substitution of one of these. Actually, let me redraw this out here. We're going to draw this out as in Cl and Cl. And essentially, we get one of these guys that switches with one of these hydrogens, and we result in dichloroethene. Okay, and again, in this case, we swapped our chlorine. Actually, we swapped our other hydrogen here. Based on the diagram, we swapped this guy in. Okay, so what we get here is we get our original molecule plus this chlorine has added in here, plus our original molecule. I'll try and draw it consistent here so it all makes sense. Again, we just substituted this chlorine in for this hydrogen, so what's left behind? Well, we still have one chlorine, and we have one hydrogen. Okay, so we have this, in this case, we have 1,2-dichloroethane. Okay, so 1,2-dichloroethane. And again, we're dealing with an alkane or an aromatic. Okay, in this case, in my example here, we're dealing with an alkane, and we substitute one of those atoms for a different entity. Okay, our next organic reaction to look at is called an elimination reaction. Okay, this involves eliminating atoms or groups of atoms from our carbon chain in our organic molecule. Now, sometimes we call this a dehydration or a condensation reaction because water is often a product of these reactions. So we see that water can be a result. And again, that elimination forms water. Okay, we've eliminated something. Now, this also looks sort of like a decomposition, and in some sense it is, but we don't call it decomposition, we call it elimination. We're pulling some sort of entity out of our compound. So this is a typical example. We would start with an alcohol, whatever the alcohol might be. It might be ethanol, propanol, butanol, anything like that. And essentially, based on the breaking of the bonds and reforming of bonds, we get an alkene plus our water. So again, we take a hydrogen out, we take a hydroxyl group out, forming water, and resulting in an alkene being formed. Okay, so we can take a look at this example. We have a couple different types of elimination reactions. Both of these two general types of elimination reactions you should jot down and you should know for any sort of exam that we're dealing with, especially a diploma. So what we see here is my first example. We start with an alcohol, and we get alkenes and water. So again, we have this, we get this hydrogen and hydroxyl group being pulled off using a catalyst. Okay, and because those things get pulled off, they form the water molecule. Okay, again, this was eliminated or pulled out. And what we see is that we get the formation of a double bond. So the electrons that were originally shared in between this hydroxyl group and the carbon, as well as this carbon and the hydrogen, are now being shared in between these two carbon atoms. So again, the electrons that were here and here are now shared between a bond in between these two carbons, forming an alkene from generally an alkane. Okay, now what we see too is if we add a base, a strong base, meaning a hydroxyl or a hydroxide, with an organic halide. So again, we have some sort of halide. Now X here that we have represented, this is our halide. Okay, so we have, say, in this example, it could be chloroethene or bromoethane or whatever it might be. And we add a strong base. Again, this is our base. And we get the formation, again, an alkene, plus our ion is displaced. So we have displaced this ion. Okay, this halide. So again, this is our halide ion. So whether it be chloride ion or bromide ion, whatever it might be, and we get, again, still this elimination of our water molecule. Okay, so this is eliminated, and we still have our halide that's eliminated, or our halide ion, still forming an alkene with our double bond here. And again, both of these general types of elimination reactions you will need to be quite familiar with going into any sort of exam. Okay. So again, we have ethanol. It gives us ethene and water. So if we take a look at that example, we get, I'm just going to zoom in so I have lots of space here. Ethanol gives me ethene, and actually I'm just going to do this and make these two a different color so we can see. So then we get the formation of ethene, like so. Bond angles dictate that it should be some sort of shape like this, and we get our HOH, or our water. Okay, so that again is an elimination reaction. We see that water is eliminated or formed. Okay, we can also see this other example here where we have our chloroethane. Okay, we have our chloroethane. So we have here we go, chloroethane, and our hydroxide ion. And what we see is we get ethene formed. And I'm actually just going to do this, make this a new color here. And I'll make this hydrogen also a new color so we can see what happens here. So we get ethene formed. Again, looks something like this. And our chloride ion, so we have plus our chloride ion, which is eliminated or displaced, and then we get plus our HOH, okay, formed as a product. Again, these two elimination reactions should be quite familiar with you as we go through. Okay, one of our last reactions that we take a look at, this is more of a complex reaction. It's called an esterification reaction, and this is essentially the formation of an ester. Okay, and the formation of an ester occurs in some form of an elimination reaction, in the sense that we have water formed. Now, this is again something that we call condensation reaction. We get water pulled out of our reaction. Now what we see here is we start with a carboxylic acid, and our carboxylic acid is sort of our parent chain. We'll call it our parent chain. And our alcohol group is joined in to that carboxylic acid to form an ester. And again, this alcohol group is our branch, and our carboxylic acid is sort of considered our parent chain. Okay, now I might jot that down because it might help you figure this out as we go through. So this is our parent chain. Whoops. Parent chain, and this is our branch. Okay, and you can kind of think of it like that as we go through in terms of naming. That might help you a little bit. And obviously note that we get water produced as a product as well. One thing you may want to note is that often heat and sulfuric acid is needed for this reaction to go forward. However, it's not always necessary, but it is good to know. Often they'll put that in sort of a diploma question, and it'll come up that you need to know that in advance. So let's take a look at some of these examples. So if we have butanoic acid and ethanol, let's take a look at how that works. Okay, so we have, and I'm going to draw them in different colors so you can really see where these hydroxyl groups are displaced, and also where we get the formation of our ester in the end. So we follow this general formula that I have on the top there. Butanoic acid, meaning I have but, 4 carbons, double bonded O, single bonded hydroxyl group, okay, and then the rest of these are hydrogens, and I'm not going to fill the hydrogens in as I mentioned in my previous lessons there. Okay, then I have my ethanol. Okay, so then I see that this forms an ester and water. So what actually happens here is that we have this hydroxyl group that is removed, plus one of our hydrogens, which exists here, for example. Okay, and this is a hydrogen. He is removed also, and we get the formation of water, HOH. Okay, and again, one of these is from our hydroxyl group that's removed from our carboxylic acid. Now, because, and actually, hold on, let me go back. This isn't quite right. We have this hydrogen, sorry, that is removed. What's going on here? This hydrogen, that's removed. So we get our HOH, okay, that is removed from this type of entity. Now this oxygen here, all of a sudden has extra bonding electrons that wants to form another bond. Same with this carbon over here. It has extra bonding electrons that wants to form another bond. So essentially, this edge of this oxygen molecule is attracted to this part of this carbon molecule to form this ester. So this is where we would get our ester formed. Okay, we still have bute, so we still have 4 carbons. We still have our double bonded O. That hasn't changed. Okay, what has changed is all of a sudden we have an O from our alcohol that's bonded here, plus our ethanol. Okay, so this is our ethanol, the purple. Notice it's consistent with the previous side here. So we have our ethanol that bonds to our ester. Now we know that esters, the functional group, is considered a COO group, which is this section sort of in here. We see that it's a COO group, okay, meaning that this is our ester. So we have the formation of our ester from our butanoic acid and our ethanol. So what we would call this, again, remember that our alcohol is sort of like our branch. Okay, this is our branch. Okay, branch. And this is our sort of our parent chain. And I just say that because it helps us with naming, remembering which portion is our parent chain. Now, again, one thing you can consider is the butanoic acid is the part that sort of remains the most consistent. And again, that's our parent chain. So we would call this, okay, ethyl, because we have this ethyl branch from ethanol. So we call it ethyl. Okay, ethyl butanoate. Now, you might remember from our previous lesson on functional groups that esters end with our -ate, which is the suffix on that type of compound. Ethyl butanoate. Again, ethyl being the branch from our alcohol or our ethanol, and butanoate from butanoic acid. Okay, let's take a look at this next example with benzoic acid and propan-1-ol. So we have benzoic acid. Okay, and propan-1-ol. Again, we get the formation of water from our OH and our hydrogen there. Okay, so we get HOH formed, or water H2O, whatever you want to call it. And then we get and this guy has our, and actually I did those little boxes different here. This is, here, I'm just going to erase this here. The water is actually formed from this hydrogen and that hydroxyl group. Okay, so we get our okay, so in this case, when we go to name this, again, we have our COO group, which is there, okay, and we call this propyl from our propan-1-ol, propyl benzoate. Okay, propyl benzoate is what we would name that esterification reaction with benzoic acid. So it's benzoate. Okay, so one other thing that we need to take a look at in this lesson is how boiling points are affected by our organic compounds and how it depends on branching as well as other components that could affect our boiling point. Okay, so intermolecular forces influence the attractive forces, and it will depend on the functional groups present, obviously, with intermolecular forces. Remembering that our ionic bonds are stronger than hydrogen bonds, which hydrogen bonds are stronger than dipole-dipole, and then we have van der Waals dispersion forces, or in other words, London dispersion forces. And the influence of these attractive forces will influence, I guess I should say, the boiling point. So the more intermolecular forces, the higher the boiling point that there would be. Okay, so higher boiling point. So if something is polar, you will have a greater boiling point than something that is nonpolar, again, based on intermolecular forces. Okay, boiling points also increase as the number of carbons increase. You can imagine there's more covalent bonds in that molecule, holding it together, requiring more energy to break it apart. So more energy means a higher boiling point, as well as branching decreases the boiling point. Again, because you have an impact on neighboring electrons, certain electrons will push against each other and sort of create a greater ability to break apart. So branching decreases boiling point rather than increases boiling point. So a longer chain with less branching will have a higher boiling point than something that has a great deal of branching on it. Okay, and that also can be for our previous lesson. We talked about how branching also affects things like octane number when we're dealing with combustion of these organic compounds as well. Again, don't forget about solubility, about how solubility is affected by polarity of molecules. So if you have a polar molecule, it's going to be able to be soluble in water or any other polar solvent, as well as if something is non-polar, it's generally soluble in a non-polar solvent. So you have to think of those things. That's an important part of organic chemistry when it comes to industry and using solvents for extraction of organic compounds, especially in the oil and gas industry. Okay, at any point that you need to go back and review these reactions, I would definitely recommend doing that. I would take a look at some practice questions, likely online or in a textbook, so that you can get some help with identifying these types of reactions and be pretty familiar and very consistent with knowing the types of reactions that they are, because you will for sure be asked this on an exam as well as on a diploma. So, good luck!